With 3 videos about ellipses, we said a lot about A's, B's, C's, that's the focus, D is the distance to the directrix, and eccentricity equations abound. But what about the other conic sections? Let's give some respect to hyperbolas, like this one. Wait, is that really a hyperbola? Well, it has the asymptotes, but what about these? Put them on the list. With parabolas, like y equals x squared, it's called a conic section, but its equation doesn't seem to fit with the others. Why is that? And can we harmonize this family? That's where we're going, so let's get started making this look like that with rotation. Like here, it's the same point, same distance to the origin, but different axes. There's the angle, and 2 key triangles. The thetas rise and fall together. All right, axis 1, x1 cosine and sine, y1 cosine and sine, axis 2, x2 as the sum of 2 pieces, y2 as a difference. It's a little harder to see maybe, but there it is. And if we are rotating from the graph on the left to the one on the right, theta is negative 45 degrees. It's our first chance to do some algebra. We'll do more later, and the form fits. And that means we can analyze this hyperbola, finding A is the x-intercept, C is the distance to the foci, E, remember that value, and D lets us draw the directrix so we can pick a point, solve for y, right, and test the equation. It works. Try not to seem too surprised. But what if we revert to our old form? Can we still show that it works? That's a little bit harder because the directrix is now slanted, so we'll need this, the equation for the perpendicular distance from a point to a line. There's the point and here's the line, complete with the equation. Rearrange it to y equals mx plus b to find and to use the slope, negative a over b. Similar triangles, and that means ratios. Notice how y naught is on the line so we can rewrite it in terms of x1. Neat. And it cleans up nicely. I'm not skipping steps here. I promise you can check it out. Anyway, let's use it. Pick a point, regain focus, equation for directrix, rearranged, and we are ready to go declare success. And try out our polar equation. It's the same shape, but recall that the center of this graph is at one focus, and that is this far from the old center. And what is d prime again? Oh yeah, it's the distance from the focus to the directrix. That's what it looks like on an ellipse where d is greater than c. Hyperbolas, however, have smaller d's and bigger c's anyway. D prime shows up in part 2, so we'll need it, and we'll also need f, the distance from the focus to the x-intercept. We are running out of letters. But in summary, this is definitely a conic section. But what about these? Racing through the details, the answer again is yes. In fact, they are all the same hyperbola. It's the same shape anyway, just different sizes, different magnitudes. They do have, after all, the same asymptotes, and we can write out an equation for these 2 lines in terms of A's and B's. Good to know. We cannot, however, say the same thing about this type of equation. It's not symmetric, and if alpha is not an integer, half the graph disappears. Where did it go? And why do you care about all this hot air? Well, because of hot air, thermodynamics, and ideal gases, shown here on a pressure versus volume graph. 4 different processes. We'll focus first on the isothermal. Temperature stays the same. So according to the ideal gas law, y times x on our graph, y times x is constant. It's a hyperbola. And I already kind of knew that, but we did prove the snot out of it. My real question was about this, about adiabatic processes. I found a place online calling them, quote, steep hyperbolas, with scare quotes. Now, a steep hyperbola sounds like redundant to me, but are they true hyperbolas? And I did a video already about adiabatic processes, it's called entropy 1, and the punchline is T times V to the gamma minus 1 is constant. Never would have guessed that. A few more steps and we'll have this, and that means we've proved that adiabatic functions are not true hyperbolas on a PV graph. So it kind of sounds like at this point that I did all that work just to find a tiny little fault with an online textbook, which kind of makes me seem extremely petty. So I better redeem myself in the next part by finding some harmony among the conic section family.